This is Professor Corey with a mini lecture on the Common-lon Effect as it applies to buffer systems. Using Le Chatelier's principle, we can predict the direction of shift if we disrupt an equilibrium. The equilibrium shown is the hydrolysis reaction for the weak acid HF. The conjugate base is the fluoride ion. If we add additional fluoride ions, the equilibrium will shift to the left to reduce the additional ions. This process will consume the hydronium ion and produce additional HF and water. Since we are reducing the quantity of the hydronium ion, it is predicted that the pH will increase or become more basic. The solution given is ammonium chloride. This is a salt. When given a salt solution, break the salt into its ions and react each with water. The chloride ion would react with the H+ from water to form HCl. This won't happen because HCl is a strong acid which by definition will completely ionize in solution. The chloride ion is considered a neutral ion. The ammonium ion will react with water to produce the conjugate base ammonia and the hydronium ion. Adding conjugate base will force the equilibrium to shift to the left using additional hydronium ion and raising the pH. Answer A is correct. This solution is acetic acid, a weak acid. Start by writing the hydrolysis reaction. The reaction produces the conjugate base, which is the acetate ion, along with the hydronium ion. Sodium acetate is a salt. The sodium ion is neutral and will not affect the pH. We know this because when we react the sodium ion with water, it'll try to form sodium hydroxide, which is a strong base that will completely ionize in solution. The acetate ion is not a neutral ion, and it's part of the buffer system. Increasing the acetate ion will cause the equilibrium to shift to the left and consume hydronium ion to do so. The loss of hydronium ion makes the pH increase or become more basic. Ammonium chloride is a salt. We will have to examine both ions. The chloride ion is a neutral ion. When we react this with water, the reaction would produce the strong acid HCl, which will completely ionize. The ammonium ion will react with water to form the conjugate base, ammonia, plus the hydronium ion. Adding NaCl will have no effect on this equilibrium. Since it is not part of the equilibrium, it will not cause a shift, and if you look at the reaction of both ions from sodium chloride with water, you'll realize that it's a neutral salt. Now we're going to calculate the pH of a solution before and after the addition of the common ion F-, the fluoride ion. Since we have a solution of weak acid, we will begin with the hydrolysis reaction. Using Le Chatelier's principle, we would predict the pH to increase upon adding the fluoride ion. Keep this in mind when doing the calculation, as this can be a very good way to catch a mistake. Another point to mention is that the Ka is provided for HF, and the value is different from the value in your chart. And the reason for this is that the chart has Ka values at 25 degrees Celsius. So this experiment is at a different temperature. And the point is, if a K value is provided in a question, use it. If no K value is provided, then use the value from the chart. First, we'll calculate the pH of the HF solution prior to the addition of fluoride ions. We will use an ice table for this with molarity values. The assumption rule applies since the K value is very small. We can solve for X, which is the concentration in molarity for both the fluoride ion and the hydronium ion. Now we have two ways to obtain the pH from here. We could use the Henderson-Hasselbalch equation since we have an equilibrium value for the weak acid and the conjugate base. We would have to determine the pKa from the Ka. The other method, which is shown, is to simply take the negative log of the hydronium ion concentration to obtain the initial pH of 1.93. This makes sense because HF is an acid. Our prediction was that adding fluoride ion would increase the pH by shifting the equilibrium to the left, so let's see if that holds true. We'll use the same ice table, but now the initial concentration of the fluoride ion is not 0. The question did say that the salt potassium fluoride is added. We don't include the potassium because it's not part of the equilibrium, and it's also a neutral ion. Since the hydronium ion starts at 0, we know that this has to increase. If one product increases, the others will as well, and the weak acid, HF, will decrease. The assumption rule applies to both the weak acid and the fluoride ion because the K value is so small. Solving for X gives us our hydronium ion concentration at equilibrium, which can then be used to determine the pH by taking the negative log of this value. The answer is 2.87, which is an increase in the pH as we expected. This problem is for you to try on your own. You will have to calculate two pH values. The first is just the weak acid, HF. They gave us the molarity, the concentration, so write the hydrolysis reaction and use an ice table. For the second part, a salt has been added. Will the salt affect the equilibrium? To find out, break the salt into its ions and see if there are neutral ions or if anything exists that is part of your equilibrium. Use the same ice table, but now you will have a new initial value for your conjugate base. Pause the video and give it a try. The answers will be displayed on the next slide. Hopefully you solved this one correctly. In this mini lecture, we learned how to predict changes in pH using Le Chatelier's principle, as well as how to calculate the pH when a common ion is added to a buffer system. If you can predict the change in pH, this can be a useful check of your calculation. In our next lecture, we'll introduce acid-base titrations and how to calculate pH values during the titration. Stay tuned, and thanks again for watching the Professor's DuBois channel.